Alright, so today we'll start by talking about first-order discrete time system. Consider the following first-order causal LTI system. Y of n minus a, y of n minus 1 equals to x of n, where the magnitude of a is smaller than 1. And we know from chapter 5 that we can immediately get the frequency response of the system, like equation 6.52. And through a lookup table in chapter 5, you can also immediately get the inverse Fourier transform, which is the impulse response of the system, as in equation 6.53. Alright, then given the impulse response, we could now start to plotting the time domain property of the system. For example, we can plot the impulse response of different value of a when a is positive, and we know that the magnitude of a is smaller than 1, then the impulse response is a monotonically decaying sequence. And the smaller the a, the decaying, the faster. So here we have this example, a equals to 3 divided by 4, which is smaller than a equals to 7 divided by 8. So the 1, a equals to 3 divided by 4, decay faster. When a is negative, then the impulse response will be positive, negative, positive, negative, and until it finally converges to close to 0. We could use equation 6.54 to get the unit step response. And the unit step response equals to summing the geometric sequence. And we know the result will look like this. And then we can plot the unit step response given different value of a. So when a is equals to 3 divided by 4, it will eventually converge to 1 divided by 1 minus a, and that is 1 divided by 1/4, and that is 4. So you can see that if you follow my mouse cursor, the final value is converging close to 4 eventually. And when a is 1 divided by 8, then the final value is 1 divided by 1 minus a, which is 1 divided by 1 minus 8, and that is 8. So this step response will keep on increasing all the way converging to close to 8. And you can see that when a equals to 3 divided by 4, it converges faster than when a equals to 7 divided by 8. But they converge to different value. And then in this case is 1 divided by 1 minus a. So they're not necessarily 1. And that implies the system not necessarily have unit gain. When a is negative, the summation of the impulse response with positive, negative will make the step response to increase and decrease, and at the end it will also converge to 1 divided by 1 minus a, and in that case that is 1 divided by 7 divided by 4, and that equals to 4 divided by 7. So the value will converge to 4 divided by 7. And the other value over here, we can also see the value going up and down, and it will converge to 1 divided by 15 divided by 8. So the value will be 8 divided by 15. Okay, so it's also converged to that, and it will not converge to any value bigger than 1. Okay, so that is the time domain property. Now let's take a look at the frequency domain property, and we could take a look at the frequency response and use the Euler relationship to decompose the pure um, the exponential functions, and that we now have cosine corresponding to the real part, sine corresponding to the imaginary part, and then we can easily compute the magnitude, which is in equation 6.55, and also the phase, equation 6.56. Okay, and then we wanted to take a look at how it looks like. So let's take a look at the case when a is bigger than 0. And in particular, what will happen when omega is equal to 0, which is the lowest frequency, and when omega equals to pi, which is the highest frequency. So when omega is equal to 0, then the magnitude is 1 divided by 1 minus a. When omega is equal to pi, the value is actually 1 divided by 1 plus a. And we know a is between 0 and 1. So that means the value 1 divided by 1 minus a is bigger than the value of 1 divided by 1 plus a. That means at low frequency, the magnitude is higher than high frequency. And also, the closer the a is close to 1, remember a needs to be between 0 and 1, so that most can be 1. If it's very close to 1, then the denominator will be small, and then that means the magnitude will be large. Okay, and we can easily make the magnitude bigger than 0 dB or bigger than 1 gain. Okay, and so here are some example. When a is equals to 7 divided by 8, then the dB at omega equals to 0 is actually 16. And you can see the dB when omega equals to pi is very low, it's even negative. And when a is closer to 0, then the magnitude is flatter. Okay, so yeah. What about the phase? Here we show the phase when a is 7 divided by 8, the fluctuation of the phase is higher. And recall, this system is a non-ideal low-pass filter, and we can see that when a is equal to 7 divided by 8, the slope around omega to 0 is very large. So the time delay is very large. And when a is smaller, closer to 0, the slope is not that steep and the time delay is not that big. Okay, so we now consider the other case when a is negative. And in this case, a is between -1 and 0. Okay, so in this case, then when omega is equal to pi, we actually has a very large magnitude. And when omega is to 0, the magnitude is low. So we have a non-ideal high-pass filter. And when a is closer to -1, the higher the magnitude at high frequency. When a is closer to 0, then the magnitude is relatively flat. And here is the phase function, and we can see since this is a high pass filter, we care more about around the frequency equals to pi, and when a is more closer to -1, then the slope is larger and the time delay is larger. Now let's talk about second order discrete time system. Consider the following second order causal LTI system in equation 6.57. And this system is parameterized by two parameters. One is r. R must be in the range of 0 to 1. And the other is theta. Theta must be in the range of 0 to pi. Then we could follow chapter 5 to easily get the frequency response of this second order system as shown in equation 6.58. And we could decompose this equation into multiplication of two first order systems. Okay. So next we wanted to first take a look at the temporal domain property. So we need to convert frequency response into impulse response and then into step response. So there are different cases we need to consider. Let's assume first theta is not equal to 0 or pi. In this case, the two first order terms are not the same. Hence, we can use partial fraction expansions, hypothesize that there exists an A and B as shown in equation 6.60, and solve that A is equals to this and B is equals to this as shown into equation 6.61. So now our frequency response is a summation of two first order terms, and we can look up the table in chapter 5 and obtain the impulse response. And since these two terms are conjugates, so it will becomes a sine function divided by a sine. Okay. And in the special case when theta is equals to 0 or pi, then the two terms that multiply together are the same. Either theta equals to 0, then we get this 1 divided by 1 minus r times exponential minus j omega n to the power of 2. Or it is 1 divided by 1 plus r exponential minus j omega to the power of 2. And for both of those terms, frequency response, we could take a look at the table in chapter 5 and obtain its corresponding inverse Fourier transform, which is their impulse response, showing in equation 6.64 and 6.66. Okay, now let's try to visualize. Hold on. Okay, so before we derive the unit step response, let's just try to visualize the impulse response. And we get all three different scenarios, equations listed over here. When theta is equal to 0, the equation is this, and we have this monotonically increasing term n plus 1. We also have this monotonically decreasing term r to the power of n. That is because r must be in the range of 0 to 1. So it's when n increases, it will monotonically decrease. So here is when theta equals to 0, you can see that when r is 1/4, we cannot see the effect of this monotonically increasing term n plus 1 because r is pretty small. So some linearly increasing terms multiplied by exponentially decreasing terms, then gamma, and when gamma is large, you cannot see the monotonic increasing terms effect. When r is bigger, which is 1/2, you still cannot see it, but when r is 3 divided by 4, then it's pretty large, so the de decreasing are slower, and then you will see the first increase and then decrease. When theta equals to pi, this is our equation. It's very similar to the case when theta equals to 0, except r is now minus r to the power of n, right? So pretty much the same, except when n is an odd number, then you have negative value. So you have this positive and negative oscillating pattern. And everything in between theta 0 and theta equals to pi, we will follow this equation. And you can see that this equation has a monotonically decreasing term and a sine function. So um, it is going to decrease, but also oscillate according to the sine function. And here are several examples over here. All right, next we could derive the unit step response by taking the summation. So if it's geometric series, then the summation gives you this terms. It's more complicated for the case theta is equal to 0 or theta equals to pi. Here we're showing you the result equation. And then we could write a computer to visualize it. So when theta equals to 0, it is monotonically increasing, but increasing to different value depends on your r. If r is closer to 1, it increases to a higher value. So you can also kind of expect in the frequency domain property, r will affect the gain. When theta equals to 0, it will, if you remember, the impulse response is oscillating, so the positive and negative will cancel out somehow. So it is the step response is not going to increase too much, and shown over here. And for the other terms, we have this monotonic decreasing and a sine function, and sine function will create negatives and positives, so they will also more or less compensate out each other. So you can see the final value when it is very big is also not very large compared to when theta equals to 0. And we could take the case when theta equals to 0 and when theta is not equal to 0. And you can see that they are actually the counterpart of underdamping second order systems in continuous time, which we talked about before in this chapter. When theta equals to 0, you can see that the unit step is monotonically increasing and it reaches stationary. And this is corresponding to a critical damp case. When theta is not equal to 0, we will usually have this overshoots effect and also raining effect, and this is similar to the underdamped case in second order continuous time system.